we have discussed ARMA models and AR and MA models sufficiently. It is essential that we put our focus on some of the Varma structure of the models, and that's what we will begin from today. So number 7, the problem we were discussing in chapter 13. So we will move on from the Varma models. Number 7, the problem is STSM Varma, where it suggests to simulate t equals 500 observations from Varma 1-1 model, where y1t is Varma y1t and y2t. We have two systems of equation, and as we can see, phi 111 should would mean that lag 1, equation 1, variable 1, lag 1, equation 2, variable 2. So in both cases of autoregressive and moving average parameters, this is how the models are developed. Now like one equation on variable 2, yes, in which Vt is a bivariate normal, where the structural variance is a bivariate normal with a zero mean and covariance matrix given by the identity matrix, and the population parameters are given in table 13.2. So let's have a look into table 13.2. We're in page 43 now. If we are to go up to table 13.2, which one is the table 13.3? So 13.2, maximum likelihood estimates of Varma 1-1 model. We have the population parameters given to us here, which are 0.0, 0.6.2 minus 0.5 for the first system of equation. Then the second system of equation has population parameters 0, 0.4, 0.2, 0.6. So let's go back to page 43. Okay, compute the maximum likelihood estimates using the Newton-Raphson algorithm. Repeat using t equals 1000 observations. Discuss the asymptotic properties of the maximum likelihood estimator. So as we can see, we will need to simulate this problem and solve our problem with simulation. So on the simulated data, perform Euler and Wald tests of hypothesis to prove that the moving average parameters are 0. So we are not looking into the autoregressive parameters here. We need to choose we need to change our set of data by with reduced n and increased n, and prove the asymptoticity of the data, which means the consistency property of the test must be proven. Okay, so let's see how this problem goes, but before that we might want to have a look if we have discussed Varma models before. So before we begin, we need to see, obviously this is maximum likelihood estimation, so we will have local functions. First we'll start with the simulation commands. So for our for MATLAB, as we know, it's random stream set global stream random stream with MT19937AR seed 1 2 3 4 5 6 7. Well, in R it is remove object RM list is all true. Graphics of set seed 1 2 3 4 5 kind Marciana twister. This is how we have cleared our previous command, and we have also introduced simulation in the system, and then we move into the local function. First, we need to look into neglog and neglog_L. All right. So the function is neglog_L with parameters theta and y. Tn size of y, where that would be so negative neglog_L is produced here directly, where in R we will do the negative mean or the negative neglog_L in a different wrapper function. So looking into unrestricted Varma model, or the complete log likelihood function will be taken here. So first of all, neglog_L, function of by lf, which has mean of log lt by, return lf. This function will return lf. Then we move into log lt. Log lt by, a function of by starts from here. So t is equal to n row y, n is equal to n column y. E1, we will have to loop over E1, V1, V2 and LF. So here V1 and V2, because you see we are testing for, we need this besides estimation, we need this to find likelihood ratio test. So we are testing for moving over each parameters. So we have to store our data that the loop will generate with simulation. So E1 is 0, t rows 1 column, E2 is 0, t rows 1 column. Log likelihood function on the other hand is 0, t minus 1 rows 1 column, because a log likelihood function will is considering the lags here. So E1 replicate 0 t1, replicate 0 t times, replicate 0 t times, replicate 0 t minus 1 time. So the first loop over the moving average part starts from 2 equals from 2. Okay, so if we look back to our theories, we see that in a Varma 1-1 model, the log likelihood function starts from 2 to t, because 2 is s plus 1, and s equals the maximum p and q, which is 1. So 1 plus 1 equals 2, and hence we have we are starting our loop from 2 to t for the moving average part. The first loop will happen over 2 to t. So E1, first residual E1y. So first, just like any system of equation or any regular equations, we'll start with estimating the structural residual or the residual. As we can see, we have two residuals here, E1 and E2. So everything else we take on the left hand side, basically, except for this part, everything else we take on the left hand side. So I parameter 1, which is phi 1, well, no, this is mu 1, I'm sorry, this is mu 1, then phi for lag 1, equation 1, variable 2, y I minus y t minus 1, so y I minus 1 1, then psi equation 1, variable 1, lag 1, equation 1, variable 1, vt minus 1, e1 I minus 1, and then psi 2 will be b4, v2 t minus 1, c2 I minus 1. For e2y is also, or the v2 is also same, equation I2 y I2 So first column, now we are talking about the second column, so we will have the results in columns b5, b6 by I minus 1 2, which is well, this is in the second row, second column, I minus e1 I minus 1, then b8 e2 I minus 1. So this is the first loop and quite easy. And first loop over MA part for R is for I in 2 to t. Then we start defining the equations in R by I1 b1 b2 I minus 1 1 b3 I minus 1 b4 e2 I minus 1. So this is practically quite easy. Then for I2, this is the second column, so okay. Then we take E, where we combine E1 and E2, and obviously we're gonna trim the first row from both of the equations to adjust them to the size of the log likelihood function. So trim both of the so column bind. I'm gonna column bind E, both of the E V's, structural residuals here, trimming the first row out. Then we have omega, and omega is obviously, we are aware of, is VT transpose. So the structural residual and the transpose of structural residual. So E transpose T minus 1, right? Yeah, indeed. See, T minus 1, 500 observations minus 1. So T minus 1 is the equation. Omega transpose of E T minus 1. Then this was the first loop over moving average part. Then for log likelihood function, we do another loop 1 to up until T minus 1, because as we can see from our equation, we are supposed to have 1 T minus 1 in the log likelihood function, because I equals T minus 1 in the log likelihood function. So half log twice pi, half log determinant of omega, which is same, then T minus 1 V structural residual transpose, which is squared multiplied to omega inverse, where omega is basically our sigma square V. So the first one, I1, I up for all I rows for all column, I rows for all column, the whole matrix multiplied to inverse of omega. So because this is the whole matrix, we'll have percentage in R, I in sequence to T minus 1. So log likelihood function is half log twice pi, then half log determinant of omega. Then now we have the tricky part, half EI for all I rows, all columns, multiplied to matrix multiplication inverse of omega. This is basically Hadamard product, inverse of omega, Hadamard product, column bind EI1. So column bind instead of transpose I'm using, because this is column, I'm doing column bind EI all elements. So this is the trick in matrix, instead of doing transpose I do column bind. That's the learning taking from this part, and that it returns the log likelihood function, so mean of log likelihood function. Now that was unrestricted. What happens for a restricted log likelihood function? Again, I start with the wrapper function is starting with restricted log likelihood function. Define the mean first, then E1 zeros, T1, T1, just like before. What happens here is that in case of restricted Varma model, we just focus on the autoregressive part and completely discard the moving average part, right? So we have in this equation without the moving average part, we have v1 equals y1 minus mu1, y1 minus mu1 minus 511 y1 t minus 1. So everything that has moving average parameter or the moving average coefficient, we discard it. Everything else in the coding part remains same, no change. And then as we have set the footstep for our simulation, we move on. We generate the data 1000 times with initial values as for both of the equation from table 13.2 as we have seen, and we have to create 100 more observations and discard the first 100 observations. So plus 100, so y1 y2 v1 v2, right? That we will need to estimate with okay, because this is simulation, so we have to simulate our data. So y1 y2 we will have to simulate here. So zeros, number of observations. So v1 v2 we create with random numbers. v1 v2 r norm, number of observations are randomly created, or RNDN. And now we will use v1 v2 to simulate y1 y2, and so we store our simulated data zeros, number of observations 1, number of observations 1. So replicate 0, number of observations time. So for t equals 2 number of observations, because indeed our y will start from 2, because it's we have to remember t equals s plus 1, s equals 1. So 2 number of observation, and then the whole equation comes into play. T minus 1 yeah, so v1t, the whole equation, we just write down the whole equation, that's all. Both system of equation for 2 number of observations is created, and then we trim the first 100 observations. Indeed, first 100 observations are trimmed because we created another additional 100 observations. So t equals length of y, and y has the matrix, so we column bind both of these equations. Now we estimate the restricted and unrestricted model with maximum likelihood estimation. So initial values we are created already, so we make a column of the initial parameters, then options, optimism, large scale, display iteration of, then theta value, and we know on the Hessian, f in Yang, b neglog, l by b stat options. And in our options, in options function, we call the optim. The first is par, which is b star, then the function which is neglog l, then yy. Method is bfgs method. See, bb is not there because theta we do not have to mention in our options function. In R we need to mention the y's and the x's that we are estimating. So y equals y, and method is bfgs, and Hessian is true because we want Hessian. So you see, after the optimization is done in our theta parameter, from the estimated results the par values will be stored. So in f value column the value will be stored, everything that has stored in the values table, and Hessian, everything has been stored in the Hessian table will be stored. So now we can do some wall test, and the wall test for vector order or autoregressive or moving average model equation is 1 by t. The VC variance covariance matrix. We'll start the variance covariance matrix, which is 1 by t inverse of Hessian. 1 by t inverse of Hessian in both cases. So 1 by t inverse of Hessian. Now the interesting part is the wall test. So we have we have how many parameters there? We have 4 unknown parameters, right? And that we square and then and square yeah, which is multiplied to number of autoregressive parameters. So square multiplied to number of autoregressive parameters. So n square is 16 multiplied to, we have 2 autoregressive parameters, which is 2 p's. So 32. Yeah. So the equation was, let me revise that again. An easy way to do this wall test is to look back to our question where we are testing for 4 moving average coefficients here and moving average parameters. And an important thing is that we need to write down the system of equation with each moving average representation well, in a repeating manner, right? Repeatedly. So you see, first parameters are mu1, phi1, phi1 in the equation 1, phi1 in equation 2, then psi1, psi2, psi1 in equation 1, psi2 in equation 1, psi1 in equation 2, psi2 in equation 2. So we have actually 2 autoregressive parameters and then 4 moving average parameters. The first moving average parameter, second moving average parameter, third, fourth, right? So this is psi1, yeah, 1 2 3 4, because we have 4 moving average parameters and 4 moving average parameters. We need to go back to the equation to understand that. So 1 and 2, then so this one, this one, this one, this one, right? But what are the unknown parameters here? This one. We also have the constant you cannot forget about. So this one, then this one in the first equation, right? So constant autoregressive parameter, first one is 1, then the second moving average parameter, and then for the autoregressive term, because it's a AR1 process, everything comes up again. Yeah. Or we can think it in a sense, for the autoregressive term everything comes up again. Yeah, think it like that, it will be easier because we have done some indexing. Then again from that equation, now this time we are setting psi 1 1 2 to 1, and rest is 0. For the autoregressive term, everything comes up again. Then again mu1, then the autoregressive parameter psi1, psi2, and then the in the second equation mu1. So first system of equation, second system of equation, first system of equation, second system of equation, first system of equation, second system of equation, mu phi psi 1 psi 1 to 1 and psi 1 to 2. Very simple. And then we are testing those for zeros. So you have r theta minus q inverse of r vc r transpose and r theta minus q transpose. So we create a matrix. First we create a column or indexing all the elements, and we put them in matrix function where we want 4 rows and number of rows will be by t's, by row is t. Q is we column bind the zeros, then W or E is we have T, R multiplied to theta minus Q multiplied to Hadamard product inverse R variance covariance R multiplied to R theta minus Q. So VAR test, and then we do P chi-square omega rows for columns. Then we are to do the restricted model. So as we are looking into the restricted model, we have initial values mu1 phi 1 1 1, mu2 phi 2 2 2. So you see we're not taking everything in the restricted values, we just taking up until the equations, the elements that doesn't have moving average parameter with them. And then we optimize it, same thing. And then likelihood ratio test. As I said, we do likelihood ratio test, which is the difference 2t minus 1 and the difference. So you see we could do VAR test with the given information on the unrestricted R, because we are using theta that we have estimated, we are using R from here, we are using Q from here. VC is also used from the optimization. So you see, but for likelihood ratio test we need unrestricted and restricted, and we use them. So P chi-square, 4 degrees of freedom, because we have 4 variables here, so 4 degrees of freedom. And Cascade also we have 4 degrees of freedom, because well, we are dealing with Varma 4, because if we take the difference, how many are we deducting in unrestricted and restricted? Our total number of moving average parameters is 4. We are testing for 4 moving average parameters, so 4 degrees of freedom. Or in another word, if we take the difference between the equation, the unrestricted and restricted, that is 4. So very simple. So that concludes Varma model. Then we can move into the next one, which is, so basically this is just, next you can just simply change the number of total replications, and it'll be quite easy. Testing Varma models for non-linearities. This is getting even more interesting. I think everything else in this problem will be quite same. Simulate t equals 500 observations of Varma 1-1 model set out in the previous exercise using the given population we just discussed. So besides this, we have a non-linear parameter, okay, and that is delta 1 y1t minus 1 v1t minus 1 y2t minus 1 v2t minus 1. So we have a non-linear time series model. The inclusion of non-linearities yields a multivariate bilinear model that is studied in greater detail in chapter 19. Perform LR and VAR test of multivariate bilinearity. Well, chapter 19 is something should be quite interesting. Let's see what is discussed in chapter 19. So here I had a small trip to chapter 19, and that is quite interesting. Basically in chapter 19 we discuss nonlinear time series models, where here we are talking about stationary time series, and non-stationary time series models are where we do unit root and co-integration and stuff like those. However, in nonlinear time series model there are two types. One is, first of all, we introduced nonlinearity to the systems of equation that we are discussing, and we derive artificial neural networks by introducing nonlinearities in our time series equation. And then in the nonlinear variance model we have Garsh, eGarsh or Arsh volatility estimation methods that are also quite fun and interesting to learn. So we will go through those later. First, let's look into the our number of observations, our problem at hand. So inclusion of nonlinearities yields a multivariate bilinear model that is studied in greater detail later. So we want to check VAR test on nonlinearities, briefly discuss how you could make the multivariate test of bilinearity robust to non-normality. Okay, let's have a look into the equations now. First of all, indeed, we need local functions, log likelihood functions, the subroutines basically, and we had simulations. We bring everything that we did in Varma, the previous problem. We said seed, and then the unrestricted model. Again, we estimate unrestricted model. Just like before, everything else remains the same. You see, we define residuals for t and one structural residuals. We estimate structural residuals for 2 to t, and we define log likelihood function to be 1 to t minus 1. And because still that there is no change in dimension, you see, in the structural residuals and log likelihood function, because our loop starts from 2 here in log likelihood in our structural residual. However, an additional parameter we will have is the nonlinearity parameter b9 and b10. I minus 1 first row, first column, I minus 1 second column, that's all. And besides that, everything else will remain same. So we'll do column bind the residuals, then we do transpose, we do omega, and then we estimate for the exactly same log likelihood function, where we know the instead of transpose we use column bind, and then we take the f, we take f negative minus mean log likelihood function, and return this neg log L function will return f. So instead of splitting the subroutines into two different subroutines, we can do it in just one way, in just one subroutine. That we should have been doing throughout the entire period. So as you found LF, you take the mean of log likelihood function and minus mean of log likelihood function that you are interested to find, and that is your unrestricted Varma. In terms of restricted, again everything else remains same, but what is missing? We will not be having the moving average parameters, that's all. Okay, I'm sorry, we will be having moving average parameters, but we will not be having the non-linearity parameters. So without the non-linearity parameters, we again to the equation, and then we go back to our problem. We use the same initializations, then we again, just like before, we randomly generate residuals first, and then we use those randomly generated residuals to randomly generate our y's, dependent variables, for 2 number of observations. However, in both of these equations we don't have the non-linearity parameter, right? In our simulation we don't have the non-linearity parameter. Without that, okay, that is one important thing we need to remember. For here we are not including non-linearity parameters, and I am at all not sure why we are cutting off the non-linearity parameter. So for simplicity's sake, because our non-linearity parameter we are restricting our non-linearity parameters only, because we're restricting our non-linearity parameters only, so we are cutting off non-linearity parameters. And for non-linearity parameters we take two initialization in our unrestricted model estimation, two initial values which are 0.1, 0.01, 0.01, that are kind of assumptions. So then we run our estimation. Now we have variance covariance matrix from all test, and we have our theta estimated. We have our Hessian estimated. Hessian we use for variance covariance matrix, and theta we use in our actual world test equation. Now we just need to define R and Q. So basically, because there is two non-linearity parameters we are interested in, you see, just the two non-linearity parameters we're interested in. In the first one we are doing joint estimation. Here we're jointly testing. So the first one is for the first non-linearity parameter, second one is jointly first and second non-linearity parameters. And so we do it obviously 4 degrees of freedom, because well, if we take the difference, there is very high chance that we will be losing 4 you know, from unrestricted to restricted, we'll probably be losing 4 elements. So you see, these are the elements we are concerned with. So 4 elements will be lost, so degrees of freedom will be 4. Now when we are looking into the restricted model, without the without initializing the nonlinear parameters, we do the regular optimization. We do the regular optimization and we do the likelihood ratio test. So that was not difficult. The only difference from previous one and this model is the introduction of nonlinearity parameter and testing the validity of the nonlinearity parameters. And while that changes the shape of world test, we do a world test jointly compared to before, and that is something we should not forget. And otherwise everything else remains same. One thing to learn is that in case of nonlinear parameters, the degrees of freedom is basically twice the actual degrees of freedom, but the degrees of freedom should have been 2, because the differences should have been 2, but this is 4. Why this is 4? Because the nonlinearity coefficient is a fact on more than one variables. So number of variables that are falling under the grasp of nonlinearity coefficient will be numbered 4. So basically that is the difference between these two problems. And then we move on to finite sample distribution. Now the problem is STSM finite, where we talk about finite sample distribution. We need to again simulate an autoregressive one model, a very simple model in which our structure residual is ID with 0 mean and 1 standard deviation. The parameters are given to us. We need to choose 20,000 replications of a sample size of t is equal to 50, and well, to initialize various autoregressive parameters are given. We need to compute the finite sample distribution of the maximum likelihood estimator of phi1 and show that this estimator is biased downwards with the size of the bias approximately equal to twice phi1 divided by t, given by Shenton and Johnson. Show that the bias decreases as the sample size increases by repeating the number of replications. T equals number of sample size, T equals 100 and 500. And so let's just jump into the problem. STSM finite and there is no local function. It is quite straightforward. Obviously, because we know we need to simulate our data, we'll start with the simulation initialization. We initialize simulation as we already know how to do that. Then we generate the data. First, our sample size is 50. Our sigma v is given to us, which is 1. Our variance is 1, 0 mean 1 variance. Our phi1 is 0.9 and number of draws is given to us. So we're taking the first any phi1, we're taking any phi1, so we're just taking 0.9 randomly. And then maximum likelihood estimation of our theta parameter will be zeros, stored in zeros. So we want theta to have number of the size of the number of the replications. The vector will be size of the number of replications in one column. So replicate 0 in draws for our theta. And this is a progress bar, text progress bar, which is minimum 0, maximum is number of replications. Style, you can choose any. The function command is text progress bar. This appears twice. You put everything in it and it closes. You can close text progress bar, and after your equation you set text progress bar with the variable and number of eyes. That's all. So for I equals 1 to number of draws, or for I in sequence of n draws, we do what? We randomly generate our residual, which is square root of sigma v, obviously square root of sigma square v, or the variance multiplied to random number t101 rows 1 column, because we have to discard the first 100. That's how we roll, and that's we did here as well. Square root of variance multiplied to r norm random number, or r norm t101, t plus 101 and 1 row. Then y is zeros, length of our residual, length of vt rows 1 column, or we replicate y because we're gonna estimate y with another loop, which will take the size of the residual. So that's all. And then we're gonna store yt. So we are gonna simulate the AR1 model, which will start from 2 to length of the residual, which is simply the simple equation, and then it will simulate up until it matches the size of v. So for 1 to 2 in 20,000 we set the residual, and for j is equal to 2 to obviously the size of v, which is 2000 again, which is the size of b is t plus 101, number of t is only 50. Okay, so it will create same sized y 50, but it will do the whole estimation 100,000 times, and this equation. So we put the whole loop under a regular function. We trim the 101, the first 100, because we replicated our residual with first 100. And conditional maximum likelihood estimation is simply regression of trim yt01 and yt10, which is yt and yt minus, this is yt minus 1, this is yt. So yt10 regressed on yt01. So this is yt, this is yt minus 1, yt minus 1. So that is conditional maximum likelihood estimation. So what we just showed here, that without defining in a simple system, without defining a maximum likelihood equation, we can simply do OLS to do maximum likelihood estimation. Why? Because you see, we talked about this before. When we have only autoregressive parameters and not moving average parameters, or autoregressive parameter gives us exactly the same estimates as a maximum likelihood estimation would do. So maximum likelihood estimation is completely unnecessary if we don't have moving average parameter and our OLS is efficient estimated. In case we have moving average as well, then we would need to do maximum likelihood estimation as before, but not in this case. So that is it. And then compute statistics, which is mean squared error and root mean squared error. Mean squared error is your theta parameter minus phi, mean of theta minus phi, phi1 squared. Something we need to we have just learned and we should remember, our estimated parameter minus phi1 square. And this is a simple regression because yt equals xyt minus 1. So we are regressing x on y, or yt minus 1 on y. So yt minus 1. That's all. Very simple OLS regression. Something else to learn from this finite sample distribution is important, is that number of draws, whenever we are talking about number of replications, that is a block. Inside that whole block, we completely generate a different code for the number of sample size. So here we generated randomly residual for the number of randoms, for the number of size 50, and we completely discarded anything in regards to number of replication. Just forget about it. Then for residual, just like a regular loop, in a regular way with the residual, with a loop we generated y. So we have 50 v's, we have 50 y's, and with that we have 50. With that we have yt, right? So we have 50 b's, we have 50 y's. With that we have yt. Up until this we don't need any parameter estimation. Then we estimate 20,000 parameters. So we estimate parameter for just one parameter with the regression, and that we do for 20,000 draws, right? Or 100,000 draws. We do that for 100,000 draws, and so we store 100,000 draw in zeros. That's the main game here, right? So here again we'll have 100,000 MSE, 100,000 RMSE. Mean is mean, bias is, well, we talked about theta minus phi1 square divided by t, or mean theta minus phi1 is conditional. Bias is 2 phi by t, 2 phi1 by t. That's all. So quite easy and quite productive. STSM finite. Now the next problem with a sip on the coffee is lag length determination. Now we need to simulate a AR3 model. Again, we don't have any moving average parameter, so it's not completely necessary that we do maximum likelihood estimation. Simulate AR3 model 200,000 times for a sample size of t is equal to 200. So when we have similar opportunities to do a loop over our dependent variable 200 times, because our residual will also have the size of 200, then we put our parameters will be estimated 2000 times. So you estimate a parameter once, then you put it in a big loop of 2000 times. For each replication, estimate AR1 to AR7 models. Okay, so first we're just gonna do AR1 to AR7 models and choose the optimal lag structure based on minimizing AIC, HIC and SIC. And then we do it for higher sample sizes, that's all. And we know that we have studied before the AIC, HIC, everything, Sakaic's information criteria, Hanna information criteria and Schwarz information criteria as equation. We are familiar with these equations. We studied them before. And so in case of optimal choice of lag order, so this is the problem actually. 13.99 VAR model of United States. So log likelihood information, log theta, which is n by 2 1 plus log twice y minus half log. So mean log twice y log determinant of omega, and then k by t minus s, k by t minus s with the log parameter, k by t minus s with the log parameter. That's all. Very simple to remember, right? We have also proved that instead of using log likelihood function, we can use it log of omega. So let's see, with all these, can we solve our problem? So the problem is titled STSM lag length. We don't have any extra functions, any local functions, but we will have replications, so we'll have to remember that. So we'll start with initializing the random command, then our parameters are introduced, 2000 replications, 300 times, P max is 7, which is maximum lag is 7. Okay, so we'll create a loop inside the loops to do this estimation 7 times. Phi 1, phi 2, phi 3, mu, these are initial values given to us. So let's create for the let's create 3 variables: a count, s count, h count. Archaics will do for 7 auto regressions. Schwarz will do for 7 auto regressions, and Hanna will do for 7 auto regressions. Before we do the looping, let's see inside what's inside the loop. So just let's forget about the replication and create the code inside. First you generate your data residual, which will be given to your number size of your sample size. I equals 4 to t. Why I equals 4 is a good question, because we're talking about AR3 model. That's why t equals s plus 1. S is equal to maximum number of autoregressive parameters, which is 3 plus 1, so equals 4 to t. So equation is mu plus phi 1 y t minus 1 I t minus 2. So this is the square root of 0.5 into random number. Beautiful. So random number will be generated for 4 to t times. So instead of, I could have done that in V, or V could have been random number of 4 to t, but it's not necessary. We could just do it inside. It'll create one random number, then for the other one it will create another. The system will automatically run this equation 4 to t times. So this is another example of shortcut, which is without using the residual, how we can create our dependent variable. So for we're saying that count, instead of k, we're saying that count, that's all, replicate 0t or equals in 4 to t. We write this equation, then this is done with our, we get yt for like 50 or 100 times. Then we set up the lags to make sure that t is constant. Y lag matrix yt is 0. Now this is something we are using for the first time, and the question is, what is lag matrix, right? What does lag matrix do? Lag matrix is, well, to understand lag matrix we need to talk about the chapter next that we will be talking about. We'll need to open that chapter, which is located here, VAR. Okay, where here we have lag matrix. Lag matrix is simply a function that takes your level, your first difference, your second difference, and for that it generates a pair of series. So x, then -1, -2, a lag. So it takes your first difference and put the first row to none, then put the first two rows to none. Then we need to actually do something to get rid of these nuns. So basically that's lag matrix, quite simple. And then we will also have to look into VAC model, but that we will be dealing with. VAC model will something we'll deal with later in the next chapter, not this one. So lag matrix yt 0, which is first our yt variable and minus, a series of minus or negative. Then because we have 7 autoregressive parameters, that will be creating 7 similar pairs. Okay, and y lag, see, replicate none, not available. Y lag, okay, so you see is different here in R. Y lag first replicate 7 times, NA will be replicated 7 times, and that first 7 times NA will be replicated, and then we will have YT, so that is in a column. Embed y lag p max plus 1, so something called embed. Let's see what embed is. Embedding a time series embeds the time series x into low dimensional Euclidean space. Each row of the resulting matrix consists of a sequence xt minus 1. So xt minus dimension plus 1, what is the original index of x. X is a matrix, x contains more than one variable and it consists of the ith observation of each element. So x embed x3. Basically xt minus 1. So if dimension is 1, xt minus 1 plus 1, which will give you xt. So this is embed. So we'll do embed here, something new we just learned. I never came across it. I'm familiar with lag matrix but not embed function. So this is amazing, right? Y lag, then 7 plus 1, embed, so 7 plus 1 minus 1, which will give you 7. Good. We'll have to, like, it does what lag matrix does, as I can probably, that's what I'm trying to say. And then after that we trim the first 100 observations, not a big deal. Then loop over the lags. X, Schwarz, Hanna, y, tt length of y is equal to p max plus 1, x, y, k, and then regular regression and the residual. With that we do log ee divided by dt, which is omega, basically. Log v squared divided by t, basically that's what it is. Yeah, omega. So this is slightly more difficult. The steps are, first you do y, you estimate your dependent variable. So you have the dependent vector now, that is starting from 4 to t, that is the size. Then you do lag matrix and you use it somehow. Okay. After you do so, you have created one vector. You make the dimension of the vector to be the column size of 7, at least 7, or maybe it can be 14, up to 14 as well. So you make a matrix here. From a vector you make a matrix. You do that, then you do the loop on X and Schwarz and Hanna. How do you do the loop here? Because j starts from 2, t minus 2. Basically this is log likelihood function, and we know that in estimating estimating autoregression or moving average parameters we do start from 2. So and then in log likelihood we do 1 to t minus 1. So 2 to p max plus 1. So x is 1s, and y lag 2 to j. So everything is from 2 here, because in the equation that is mentioned that it will start from the log likelihood functions. Generally, I repeat, the log likelihood functions require you to starts from s plus 1, starts from 2, t minus 2 or t2, exactly the thing in the equation. This has nothing to do with log likelihood functions. Is just t minus 2. 2 is a number that is used constantly. Okay. Give me 1 second. In the meantime, please have a look into this equation. Yeah, so omega always starts from t equals 2. That has nothing to do with anything else. Whenever we are estimating omega, t equals 2, we have seen that. And when we are doing Varma 1.1 model, we have seen that our equation starts from, the log likelihood function starts from t equals 2. All right. Also, in our regular estimation, even our log likelihood functions, the part that is factorial is starting from t equals 2. The conditional log likelihood function starts from t equals 2. So this is in general starting from t equals 2. And then we do the regular regression. Fine. And then we do, because it's log likelihood function we are talking about, we take log of, we just do this from the equation, j minus 1 times, because log likelihood function is I minus 1 times, so j minus 1 times. So that makes sense. This is also coming from the log likelihood, motivated from log likelihood representation. Makes sense, right? Okay. And this is it. Here we end looping over 2 to p max plus 1. So you have a matrix sized of E, Akai's, Schwarz, Hanna. Okay. And you take the minimum of Akaik, you take the minimum of Schwarz, you take the minimum of Hanna, and maybe you just add them with 1. That is where it ends. And most importantly, we do it at the end. After we are done with the coding, we put it in a huge replication so that it continues many times. It's a bit complicated. The lag matrix is something we have never came across before, and so it is a bit interesting. It changes the dimension of your matrix significantly. So suppose you had a 2 lag matrix, so you'd have how many? 4 plus 2, 6 columns. You had 6 columns for 2 lag ones. So if you have 7, you understand how many columns I'm talking about. Quite a few, I think, because in lag matrix we're talking about the level 1. The first is level in the vector, the second is first difference, the third is second difference. So this is quite interesting. And then using the loop we create residual. In a similar manner we created AR1, and then we use the same loop for log likelihood estimation. It was slightly difficult, but it was a good learning or a different approach to look into the situation. Now, very important, grandeur causality. I want you to read the question very carefully and understand what we are going to do in this problem, because from here things are becoming very practical and, what would I say, astoundingly important. But before that, I'm just gonna draw an end to this current video before we move into discussing things in more detail.